What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. Jupiter's great red spot is shrinking. At the same time, the fastest ring of winds around its edge has been speeding up. Both statements come from Hubble, and both can be true. Between 2009 and 2020, researchers measured an increase of as much as 8% in the average speed of that outer ring. Across a much longer record, the red oval has become shorter and more circular. If smaller meant weaker in a simple way, those measurements should point in the same direction. They do not. The contradiction is our first warning that the Great Red Spot is not a single thing. It is a colored haze, a field of moving clouds, a fast boundary, a slower interior, and a vortex extending hundreds of kilometers below the level Hubble can see. Those parts can change on different schedules. Some changes last for decades. Others reverse during a 90-day oscillation. Some are observed directly. Others appear only in models. So the familiar claim that the Great Red Spot is dying begins with a fact and then outruns it. The fact is shrinkage. The unproven part is the diagnosis. By the end, we will build a stricter test for what the death of a storm on a planet like Jupiter would actually look like. We will separate the edge we can see from the circulation hidden below it. We will ask how a storm can lose width while its fastest winds gain speed, why red clouds can peel away without tearing the vortex apart, and what future observations could distinguish continued contraction from a stable, smaller form. The answer will not be a date. No present measurement can support one honestly. The answer will be a way to read the evidence without confusing a changing appearance with a disappearing storm. Start with the image that made the Great Red Spot an icon. Jupiter fills the frame as a banded globe. Cream-colored zones and rust-colored belts circle the planet. Near the southern edge of the equatorial region, a red oval interrupts the stripes. It looks self-contained, almost as if someone pressed a thumb into wet paint and left a clean boundary around the mark. That apparent boundary is useful, but it is not the whole storm. A camera records reflected sunlight. The colors in the image are created by particles and gases near the visible cloud tops, then shaped by filters, calibration, and image processing. Track small clouds from one frame to another, and the same camera can reveal motion. Observe in ultraviolet light, and high hazes become easier to distinguish. Move into infrared wavelengths, and temperature or cloud opacity enters the picture. Use microwave radiation, and the instrument can sense much deeper pressure levels. Measure a passing spacecraft with exquisite precision, and even the storm's gravity signal may appear. Each method answers a different question. None of them alone produces a complete Great Red Spot. If you value documentaries that let the evidence change the picture instead of forcing an easy ending, you can subscribe to Cosmic Drift. The red color is the easiest feature to recognize and one of the hardest to interpret. The visible oval can brighten or fade. Its outline can change as clouds form, dissolve, or are pulled into filaments. Yet a vortex is defined by organized circulation. Its dynamical boundary is traced more closely by winds than by color. The fastest clouds do not occupy every part of the red interior. They race around a high-speed ring near the outside, while motions closer to the center are substantially slower. Below that visible weather, microwave observations reveal a thermal and compositional anomaly that continues far beneath the familiar colors. Gravity measurements indicate that the mass associated with the circulation also reaches deep into the atmosphere. A patch of red haze, a wind collar, and a deep vortex can overlap without having identical edges. This makes the word spot dangerously convenient. It compresses several physical layers into one everyday object. When someone says the spot is shrinking, the first question should be which spot? Is it the area of distinctly red material? Is it the long axis of a cloud oval? Is it the width enclosed by the high-speed ring? Is it the horizontal reach of the deep microwave anomaly? Those are related measurements, but they are not interchangeable. The distinction is not a technical escape hatch. It changes the diagnosis. If red material fades while the circulation remains coherent, Jupiter has lost a color signature, not necessarily a storm. If the cloud oval contracts while the high-speed ring retains organized rotation, the vortex has changed shape without disappearing. If both visible structure and circulation weaken for years, but a deep anomaly remains, decay might be underway at one level, while another level persists. A convincing death claim would need these independent records to converge. Hubble's long view helps explain why. In 2021, a team reported winds measured from 11 observing periods between 2009 and 2020. The software followed tens of thousands of cloud vectors in each observing set. It did not infer one wind speed from the blur of the whole oval. It mapped how different parts moved. Cloud tracking begins with time. Jupiter turns once in less than 10 Earth hours, so a feature moves rapidly across the disk, even if it is stationary within the surrounding atmosphere. Researchers take images separated by known intervals, correct for the changing viewing geometry, and project the curved cloud tops onto a common map. A small patch in the first map is compared with nearby patterns in the next. The displacement divided by the time interval gives a horizontal velocity. The method must separate two motions. Jupiter's rotation carries the entire region around the planet. Local winds move clouds relative to the chosen rotation frame. Astronomers use coordinate systems designed for different latitude bands, then report drift and wind after accounting for the planet's background turn. The tracked cloud is also a tracer, not a tagged parcel. It can change shape between images. New clouds can form. Contrast can fade. Automated matching, therefore, produces candidate vectors that must be filtered for consistency. Tens of thousands of measurements allow outliers to be rejected and regional averages to be tested statistically. Resolution sets another limit. Hubble can distinguish features on the order of hundreds of kilometers at Jupiter, not every turbulent curl. Motions below that scale are blended into the visible pattern. The reported wind field describes the resolvable cloud top circulation, while smaller eddies continue underneath the pixels. Consistency across years is crucial. A different filter changes which clouds dominate. A different map projection changes local distortion. A different tracking method can shift the average. The 2021 analysis reprocessed the observing periods with a common approach and ran statistical tests on the trend. The acceleration emerged from that controlled comparison, not from placing two colorful photographs side by side. This distinction matters whenever a number such as 400 miles per hour appears. It is not the speed of the entire red oval through space. It is the motion of cloud tracers in the high-speed ring relative to Jupiter's rotating frame. The storm itself drifts in longitude much more slowly, while its internal winds race around the center. One parcel near the ring can circle the vortex, while the oval remains in roughly the same latitude band. The pattern has a translation speed, an internal rotation speed, and short oscillations superimposed. Mixing those motions can turn a precise measurement into a misleading mental picture. The same care applies to vorticity. Researchers calculate local rotation from neighboring wind vectors. A region can have fast, straight-line flow, but little local spin, or slower flow with strong curvature and significant vorticity. The Great Red Spot's identity lies in the closed pattern and its turning, not in the fastest number alone. The fastest region formed a ring near the outer boundary. Average speed in that ring increased by up to 8% during the interval and exceeded 400 miles per hour. The annual change was small, less than about 1.6 miles per hour per Earth year. No single snapshot could reveal it. The result emerged because Hubble could return with consistent resolution over more than a decade. Near the middle of the red spot, the winds were much slower. That difference matters. A giant anticyclone does not rotate like a solid plate. The cloud field contains shear, waves, filaments, and local disturbances. A speed measured near the outer collar cannot be assigned to the entire interior. The team also found an abrupt change in 2017 associated with a large convective storm nearby. That event showed that the wind map can respond to its surroundings. Yet the researchers did not find the same kind of dynamical response during the famous flaking events of 2019, when red material appeared to peel from the oval. The visible drama was not matched by an equally dramatic change in the high-speed boundary. That is our first completed result. The Great Red Spot can become visibly smaller while its outer winds become faster, because width, color, and wind are different properties of a layered vortex. This does not prove that the storm is healthy. It proves that size alone is an incomplete medical chart. It also raises a harder question. If a century of shrinkage is real, what exactly has been shrinking? And how confidently can the early measurements be compared with modern images? To answer that, the story has to move backward, past spacecraft and photography, into an age when Jupiter's weather was recorded by eye. In 1665, Giovanni Domenico Cassini described a dark oval at the latitude where a famous Jovian spot would later be known. He and other observers followed what became called the permanent spot through 1713. The name suggests continuity. The record does not provide it. After those observations, the feature was lost for well over a century. For generations, histories of the Great Red Spot often joined Cassini's oval to the modern storm. It was an appealing bridge. If the objects were identical, one vortex had survived from the first decades of serious telescopic astronomy into the age of robotic spacecraft. But a long gap is not merely an empty stretch on a timeline. It is missing evidence about identity. A 2024 study returned to the old drawings and written reports, then compared the sizes and motions of the 17th century permanent spot with the storm observed later. The authors concluded that the two were unlikely to be the same object. In their reconstruction, the current Great Red Spot was first seen in 1831, perhaps when it was still developing. The older oval probably disappeared during the interval when observers could no longer follow it. That conclusion is an inference from historical evidence, not a time-lapse film of one storm vanishing and another appearing. Early telescopes were limited. Observing practices varied. Drawings could exaggerate a contrast or compress a shape. Jupiter was not watched every night by a coordinated network. The absence of a record is not direct footage of dissipation. Yet the case against simple continuity is stronger than the gap alone. The permanent spot and the modern Great Red Spot differ in their measured motion. Their dimensions do not join smoothly into one evolution. The 2024 analysis combined those discrepancies with numerical experiments of possible formation routes. Its authors judged that the modern storm most likely formed as a long circulation cell between opposing jet streams, then became more compact as it evolved. The result removes a legend, but gives the modern storm a more defensible age. It has been observed for about 2 centuries, not necessarily more than 3.5. That is still extraordinary. No weather system on Earth offers anything close to such a continuous identity. But it also supplies a warning. Jupiter can host a giant spot for decades and then lose it. Longevity is not immortality. The old permanent spot therefore becomes our first comparison case. It may represent a vortex that occupied the same atmospheric lane and later vanished. What the record cannot tell us is how. There was no Hubble wind map, no microwave sounding, and no gravity overflight. If its color faded first, its circulation weakened first, or the entire vortex migrated and broke apart, the telescopes of the period could not preserve the distinction. The modern Great Red Spot has a far richer record. Beginning in 1831, observers repeatedly sketched and measured the oval. By the late 19th century, it became a prominent target. Measurements around 1879 place its long dimension near 39,000 kilometers. That is more than 3 Earth diameters. Modern estimates place the long dimension closer to 14,000 kilometers, near the scale of Earth itself. Those endpoints are so different that uncertainty in a hand drawing cannot erase the trend. The modern storm is far shorter than the great elongated oval seen in the 19th century. It has also become rounder. But the route between those endpoints is not a perfectly smooth line, and the measurements are not all made in the same way. An observer in the 1800s might estimate the edges of a contrast feature through a telescope while Earth's atmosphere blurred the view. Later observers used micrometers, photography, and more consistent timing. Voyager offered sharp, close views during brief encounters in 1079. Hubble introduced repeated global maps from above Earth's atmosphere. Juno added close imaging from changing geometry, though its orbit was not designed to make a uniform annual size record. Each instrument has a different resolution, wavelength response, viewing angle, and definition of the edge. A bright red core can occupy less area than a pale surrounding collar. A filament may be counted as part of the spot in one method and excluded in another. Modern image processing can trace boundaries with precision that an early drawing could never match. Scientists handle this by comparing overlapping data, preserving uncertainties, and looking for trends larger than the measurement differences. The long-term contraction survives that test. It is visible across independent records and across large changes in technology. The exact width assigned to a particular old drawing may be debated. The fact that the long axis has shortened dramatically is not. This historical record owes much to people who watched Jupiter without controlling a major observatory. Amateur astronomers can observe on nights when a professional telescope is scheduled for another target, or when a spacecraft is on the far side of the planet. Their images may not probe deep structure, but they can capture short-lived cloud changes and alert researchers to events that deserve rapid follow-up. The Great Red Spot is unusually well suited to that partnership. Jupiter is bright. Its rotation brings the storm into view on a predictable rhythm. Skilled observers can combine many short exposures to reduce atmospheric blur and reveal small-scale detail. Networks spread across longitudes can follow a disturbance while Earth turns. The 2019 flaking episode demonstrated the value of that coverage. Red blades seemed to detach from the main oval over a matter of weeks. The event looked like a storm unraveling in public. It also showed why a high-cadence visible record must be paired with other measurements. The clouds told scientists where material appeared. They did not reveal by themselves whether the underlying circulation had lost coherence. The historical record, therefore, establishes two things at once. The visible oval has undergone a real, enormous contraction. The visible oval is also a measurement shaped by instruments, wavelengths, and cloud chemistry. Both must remain true as we move from history into dynamics. Now imagine the storm not as a spot, but as a circulation cell confined in a narrow atmospheric lane. North of it, one jet moves westward. South of it, another moves eastward. Between them, the Great Red Spot rotates counterclockwise in Jupiter's southern hemisphere. It is an anticyclone, a region of high pressure whose rotation direction is set by the planet's rapid spin and its location south of the equator. The two jets do more than pass beside the vortex. They constrain its latitude. Across the reliable observing record, the Great Red Spot has remained near the same southern band even while its longitude drifted. The storm can move east or west relative to an adopted rotation system. It can oscillate. It can stretch and squeeze. It does not wander freely north or south across Jupiter. That confinement changes the geometry of shrinkage. The oval's north to south extent has remained comparatively limited by the available lane, while the long east to west dimension has contracted dramatically. The storm is not simply losing scale in every direction. It is being reshaped within a band of surrounding flow. The difference matters because a vortex carries organized rotation. In fluid dynamics, that local spin is described by vorticity. The word can sound abstract, but the idea is visible in a cup of stirred liquid. Water can move across the cup and also rotate around a local center. Vorticity measures that turning tendency. On Jupiter, scientists infer it by tracking cloud motions across the image and calculating how neighboring wind vectors differ. The Great Red Spot's strongest turning is concentrated near its outer high-speed ring. This ring acts like a dynamical collar. Inside it, the flow is slower. Outside it, the surrounding jets and turbulent clouds follow different paths. The collar helps define the coherent vortex more physically than red color alone. Jupiter's rapid rotation and stable layering also shape the storm. Warm and cool parcels do not simply mix through the entire atmosphere. Density changes with pressure and temperature, producing stratification. Rotation redirects moving air, encouraging large flows to organize into jets and vortices rather than rush directly from high pressure to low pressure. It is tempting to explain the red spot's age with one sentence: Jupiter has no solid surface to create friction. That statement contains a useful contrast with terrestrial hurricanes, but it is not a full mechanism. Earth storms do interact with land and oceans. Landfall can deprive a tropical cyclone of warm water and increase friction. Yet the Great Red Spot is not merely an Earth hurricane spared from landfall. Its scale, energy environment, vertical structure, and relationship with planetary jets are different. Even without a solid surface, turbulence can transfer energy between scales. Waves can carry momentum away. Radiative cooling can change temperature structure. Viscosity, though small on planetary scales, is not literally zero. A vortex can be strained by nearby jets, collide with smaller systems, or become unstable. Neptune provides direct proof that a giant planet without a solid surface can still lose large atmospheric vortices. The better question is not why nothing stops the Great Red Spot. Many processes can change it. The question is how the organized circulation has remained within a range that resists those losses for roughly 2 centuries. One part of the answer may be the surrounding jets. A vortex embedded between opposing streams can exchange momentum with them. The lane can prevent large latitude excursions. It can also squeeze the oval if the vortex overfills the available width. In the 2024 Hubble study, researchers proposed that the present spot may continue contracting until it fits more comfortably within the surrounding wind field, then stabilize in a smaller and less elongated form. That is a prediction, not an observed endpoint. Hubble's dedicated campaign covered one oscillation cycle. The long-term trend has not yet arrived at a clearly constant size. Still, the idea reveals why shrinkage need not imply a march to zero. A vortex can change shape as it seeks a different balance with its environment. Another part of the answer may lie in the storm's own secondary circulation. Air can rise and sink within and around the vortex, moving heat, particles, and chemical tracers between levels. That vertical motion can maintain temperature contrasts and influence the visible haze. Models have explored how such flows might help a long-lived vortex replace energy lost to smaller-scale turbulence and radiative processes. But every proposed maintenance mechanism must face the same constraint. Hubble sees only the upper clouds. It cannot watch the bottom of the storm. A trend in cloud-top wind tells us that the dynamics are changing where the tracers are visible. It does not identify the deep energy source by itself. This is why the faster outer winds are intriguing but not decisive. If the vortex were contracting while roughly conserving a form of circulation, faster motion might seem natural, much as a spinning skater turns faster when drawing in their arms. Yet the Great Red Spot is an open atmospheric system, not an isolated skater. It exchanges momentum and energy with jets, smaller vortices, waves, and vertical motions. The analogy can suggest a direction. It cannot calculate the outcome. The measured 8% increase also describes an average trend in a particular ring over a particular 11-year interval. It does not show that the winds have accelerated continuously since 1831. It does not mean every cloud moves faster. It does not prove the total energy of the vortex has increased. The team that measured the trend explicitly noted how difficult its meaning was to diagnose without a view below the clouds. So the wind record leaves us with a productive tension. The visible oval has contracted over a century. The high-speed boundary became slightly faster over a decade. The latitude remained confined. Together, these observations resemble a vortex changing geometry within a jet lane, not a structure simply fading away. To see whether that organized motion continues below the clouds, we need an instrument that does not depend on reflected sunlight. We need to listen to the heat rising from Jupiter's deeper atmosphere. Juno carries a microwave radiometer built for that task. The instrument measures microwave radiation emerging from within Jupiter. Different frequencies are absorbed and emitted differently as they pass through the atmosphere, especially in the presence of ammonia. By comparing its channels, researchers can infer temperature and composition across a series of pressure levels beneath the visible clouds. This is remote sensing, not a camera looking into a transparent hole. Jupiter's clouds do not peel back to reveal a neatly bounded column. The radiometer records brightness temperatures. Scientists then use models of how microwave radiation moves through the atmosphere to reconstruct the conditions most consistent with those measurements. During Juno's pass over the Great Red Spot on July 11, 2017, the microwave signal changed as the spacecraft crossed the vortex. The anomaly persisted down to at least the 100-bar level, far below the familiar ammonia cloud tops. The data indicated that the storm's structure extended more than 350 kilometers beneath the level, usually treated as the visible top of Jupiter's weather. The word deep deserves context. A 350-kilometer storm on Earth would be impossible because Earth's weather-producing atmosphere is shallow and a solid surface waits below it. On Jupiter, the distance is small compared with the planet's radius, yet enormous compared with the height range that produces the red visible oval. The Great Red Spot is not a stain painted on the highest cloud deck. It is a three-dimensional circulation embedded in a much deeper atmosphere. The microwave record also revealed that Jovian vortices do not all share the same depth. Some anomalies extended about 100 kilometers below the clouds. The Great Red Spot reached farther. That diversity is useful because it shows the instrument was not merely detecting one global layer and labeling it storm. Local atmospheric structures produce distinct signatures. Still, microwave sounding has uncertainties. Brightness depends on both temperature and the abundance of microwave absorbers such as ammonia. A colder region and a region with different ammonia concentration can influence the signal in partly similar ways. Researchers use multiple channels, spatial patterns, and physical constraints to separate those effects. But the reconstruction is not a direct ruler lowered into the vortex. This is why a second method mattered. If the Great Red Spot contains a broad mass anomaly associated with winds and density differences, its gravity should tug on Juno as the spacecraft passes overhead. The tug would be extraordinarily small. Jupiter's entire gravity field dominates the spacecraft's motion, and the planet's interior is not perfectly simple. The signal from one atmospheric vortex must be separated from the much larger pull of the planet. Juno's radio link made that possible. A deep space network antenna on Earth tracked the frequency of the spacecraft's signal. Motion toward or away from Earth creates a Doppler shift, allowing tiny changes in line-of-sight speed to be measured. Using two close passages over the Great Red Spot, including a July 2019 gravity experiment, scientists looked for the minute velocity perturbation caused by the storm's local gravity field. Juno was moving near the cloud tops at about 209,000 kph. The tracking system detected velocity changes as small as 0.01 millimeters per second from more than 650 million kilometers away. That is the scale of precision required to weigh the hidden circulation of a storm from another planet. The resulting analysis constrained the Great Red Spot's depth to about 500 kilometers below the cloud tops. That value does not mean a hard boundary was imaged at exactly 500 kilometers. It is a depth scale inferred by comparing the measured gravity signal with models of how the observed winds decay downward. Different vertical profiles produce different mass anomalies and therefore different gravitational effects. The microwave and gravity results are related, but they are not duplicate readings of the same property. The microwave radiometer is sensitive to thermal and compositional structure. Gravity responds to the distribution of mass. Agreement that the storm reaches hundreds of kilometers below the clouds is powerful precisely because the methods rely on different physical signals. Now compare that depth with the storm's width. Even at about 14,000 kilometers across, a 500 kilometers depth is only a few % of the horizontal scale. The Great Red Spot is deep compared with visible weather, yet thin compared with its own span. It resembles a vast rotating lens more than a vertical cylinder. Compare it again with Jupiter's zonal jets. Gravity measurements indicate that the planet-circling east-west winds extend roughly 3,200 kilometers downward. The jets that confine the Great Red Spot are far deeper than the vortex itself. The storm occupies a substantial weather layer nested inside an even deeper system of planetary circulation. This vertical geometry removes another easy explanation. The red spot does not need to be rooted in a solid surface or attached to a compact interior feature. It can persist as a coherent atmospheric structure because its rotation, stratification, and environmental flow form a self-organized system. At the same time, its shallowness relative to the jets means those surrounding currents can influence its shape and motion without becoming part of the vortex in a simple way. The depth measurement also changes how we interpret a fragment at the top. Imagine seeing a strip of red haze peel from the oval. That material occupies a thin upper region. The underlying circulation reaches hundreds of kilometers below it. Losing the strip may be dynamically important if it reflects deeper strain, but the image alone cannot establish that connection. The difference resembles foam on a rotating ocean current, with one crucial caution. Jupiter does not offer a familiar ocean surface at that level, and the analogy cannot reproduce its compressible hydrogen atmosphere. Yet foam can help us see why a tracer's shape may change faster than the flow carrying it. Whitecaps can break, join, and vanish, while a broad current persists below. For the Great Red Spot, colored aerosols and bright clouds serve as tracers. They make the circulation visible, but they also have their own chemistry and lifetimes. Sunlight alters particles. Vertical motion lifts or lowers hazes. Condensation changes opacity. Neighboring flows stretch material into filaments. A dynamical boundary, inferred from wind vectors, can remain coherent even when the colored tracer temporarily crosses or retreats from it. Juno therefore provides our second completed result. The visible oval is attached to a storm that reaches hundreds of kilometers below the clouds, and two independent methods support that depth. The red shape is not merely cosmetic, but neither is it a complete map of the vortex. This deep structure does not make the storm immortal. A 500 kilometers vortex can weaken, lose coherence, or be absorbed into surrounding flow. The measurement simply raises the evidentiary bar. Any claim of death based on a narrowing red outline must explain what is happening to the circulation far below that outline. It also introduces a practical difficulty. Hubble can return each year and map the visible winds. Juno cannot repeat an identical close gravity overflight whenever the oval changes shape. The spacecraft follows a long polar orbit, and mission geometry determines when it passes over a particular latitude and longitude. Deep measurements are rare snapshots. Visible measurements form the longer movie. Scientists must connect those timescales carefully. The deep vortex measured in 2017 and 2019 establishes structure during those encounters. It does not guarantee that the same depth remains unchanged today. Hubble's annual maps reveal ongoing cloud-top evolution, but they cannot tell us each year whether the deep anomaly changed by 10 kilometers or 100 kilometers. This gap is central to the diagnosis. Planetary science often works with instruments that cannot all observe the same target at the same moment. The solution is not to pretend the records are continuous. It is to ask which changes are slow enough to compare across years, which might reverse in weeks, and which require a future mission to measure again. In the Great Red Spot, the most dramatic example of a short timescale appeared when Hubble stopped treating its annual visit as enough and watched the storm repeatedly for about 90 days. From December 2023 to March 2024, Hubble gathered a dedicated sequence with the cadence needed to follow one complete oscillation. The telescope measured more than position. Researchers tracked the size of the oval, its ellipticity, brightness, color, and vorticity. They wanted to see how those properties changed together. The result was not a smooth contraction. The great red spot squeezed in and out. Its elliptical shape changed. Its motion alternately accelerated and decelerated. Ultraviolet observations showed that the distinct core became brightest when the oval was largest during the cycle, consistent with less haze absorption at that phase. The behavior surprised the team because earlier observations had established a longitudinal oscillation, but the accompanying size oscillation had not been measured with that clarity. The storm behaved less like a rigid oval and more like a soft object pressed between moving boundaries. The surrounding jets provide a geometric picture. The vortex sits between a westward jet to the north and an eastward jet to the south. As its motion changes, it pushes against those flows. The researchers compared the effect to filling squeezed between pieces of bread. When the center is pressed, the sides bulge. The image is useful because it shows how a confined vortex can trade length for width without losing its identity. But the cause of the 90-day oscillation remains unknown. No hydrodynamic explanation has yet tied all the measured changes into a complete mechanism. Hubble observed one full, dedicated cycle. A single cycle can establish that the behavior occurred. It cannot establish how stable its period is, whether its amplitude changes over years, or which deeper process drives it. This is where a measurement can be both decisive and limited. The campaign decisively disproves the idea that every short-term change in width is irreversible shrinkage. If the oval is caught near the narrow phase of an oscillation, a comparison with another date can exaggerate a downward trend. Yet the century-scale contraction remains much larger and persists across many cycles. Oscillation does not erase the long trend. The correct picture contains both. The Great Red Spot has contracted over the historical record, and it breathes around that evolving mean size. A heartbeat does not tell us that a body is growing. A long-term loss of height does not tell us that every inhale is recovery. Different timescales are superimposed. This helps explain why headlines can disagree while citing real data. One article may focus on 150 years of contraction. Another may report that the spot grew slightly during a 90-day phase. A third may emphasize faster edge winds. None of those statements must be false. The mistake appears when one scale is used to erase the others. The Hubble team offered a future scenario based on the storm's relation to its latitude band. They suggested that the Great Red Spot currently overfills the space favored by the surrounding wind field. Continued contraction could bring it inside that lane, allowing the jets to hold a smaller, less elongated vortex more securely. In that scenario, shrinkage is evolution toward a new balance, rather than the final stage of disappearance. The proposal is attractive because it links observed geometry to a known environmental constraint. It also fits the recent trend toward a rounder shape. Yet it remains a prediction. The storm has not announced that it has reached equilibrium. A model can identify a possible stable state without proving that the real atmosphere will settle there. Other outcomes remain open. The oval might continue to contract beyond the predicted balance. It might enter a period of expansion. Its depth could change while the top stabilizes. Interactions with nearby storms could alter the trend. The 90-day oscillation itself might vary in amplitude and make long-term size estimates noisier. The importance of the stabilization idea is not that it guarantees survival. It breaks the false logic that a decreasing quantity must reach zero on a simple schedule. Many physical systems approach a new equilibrium. A cooling object approaches the temperature of its environment without passing through it at the same initial rate forever. A damped oscillation can settle around a new value. A vortex constrained by jets may change until its geometry fits the available lane. This is also why extrapolated death dates are unreliable. Take a recent rate of width loss, draw a straight line to zero, and the arithmetic produces a year. The atmosphere does not promise to follow the line. The rate has varied. The shape oscillates. The physical boundary being measured may change definition as color, and clouds evolve. A future equilibrium or abrupt interaction can bend the trend. A disappearance date would require a model that predicts not only continued contraction, but also the failure of circulation and the deep vortex. Current observations do not provide that chain. They show a system in evolution. The 90-day campaign therefore gives us a third completed result. The Great Red Spot's apparent size can reverse during a short oscillation, and the team considers stabilization at a smaller shape plausible. Neither finding cancels the historical contraction. Both findings prevent that contraction from becoming a clock. To understand what might control the longer trend, we have to look beyond the Great Red Spot itself. Jupiter's atmosphere is crowded with smaller vortices, convective outbreaks, waves, and filaments. The giant storm does not rotate in an empty lane. It has neighbors, and some of them may be part of its energy budget. In terrestrial weather, large blocking high-pressure systems can be sustained or altered by smaller transient eddies moving through the surrounding jet stream. The smaller systems transport momentum. Their encounters can reinforce a block, shift it, or help erode it. The details differ from Jupiter, but the general idea inspired a set of numerical experiments published in 2024. Researchers used a three-dimensional atmospheric model to simulate a great red spot-like vortex. In some runs, smaller transient vortices approached and interacted with it at different frequencies and strengths. In control runs, those interactions were absent. The simulated giant vortex became stronger and larger when it received repeated encounters. Without that activity, it tended to shrink during the modeled interval. The result supports a possible feeding mechanism. Smaller storms can transfer energy and circulation to a larger vortex. If the population or path of those smaller systems changes, the Great Red Spot's size could respond. But the experiment did not travel back through Jupiter's atmosphere and count every encounter since 1879. It did not prove that a declining diet caused the observed historical shrinkage. A numerical model tests whether a mechanism can work under specified conditions. It reveals consequences within the model's physics and resolution. The real atmosphere may include additional processes or different initial states. The careful conclusion is conditional. Repeated vortex interactions are capable of modulating the size and strength of a great red spot-like system. Reduced feeding is therefore one plausible contributor to shrinkage. It is not the only candidate, and the long-term observational record of the necessary interactions is incomplete. The hypothesis nonetheless changes what observers should watch. If small vortices matter, a measurement program cannot isolate the red oval and ignore the lane around it. Researchers need the frequency, size, spin, and trajectories of neighboring systems. They need to know which objects merge, which are deflected, and which are torn apart near stagnation points. That brings us back to the red flakes of 2019. The event looked like material being removed from the Great Red Spot. In the interaction picture, some of those features may have involved clouds from smaller vortices that had not been fully incorporated. When opposing flows meet, local stagnation points can form. Material can be stretched into blades and expelled even while the primary vortex remains coherent. The visible sequence alone cannot assign every filament to a source, yet the long Hubble wind study offers a powerful cross-check. It found a notable dynamical change associated with a nearby convective storm in 2017. It did not find an equivalent change in the high-speed ring associated with the 2019 flaking. The caller continued to define an organized vortex. This does not mean cloud shedding is always harmless. A future event could remove momentum, alter the wind boundary, or trigger instability. It means that this particular visual symptom did not carry the dynamical evidence required to call it disintegration. Medicine again provides a useful structure, if not a literal analogy. A symptom matters most when it aligns with independent tests. A changing skin mark, a shift in pulse, and an internal scan each reveal different things. One dramatic surface event can motivate investigation without deciding the diagnosis. For the Great Red Spot, the independent tests are cloud morphology, wind vectors, thermal structure, microwave opacity, gravity, and long-term motion. The stronger the claim, the more of those records should agree. The smaller vortex experiments also complicate the meaning of shrinkage. A storm can contract because it receives less energy from its environment, because the confining jets favor a smaller geometry, because its internal circulation changes, or because several processes operate together. Observations have not selected one complete cause. This uncertainty is not a failure of the research. It is a map of the next measurements. A hypothesis about feeding predicts correlations between encounter frequency and size change. A hypothesis about jet band fit predicts stabilization as the oval becomes less elongated. A hypothesis about internal evolution predicts changes in depth, temperature, or wind structure even when external encounters are similar. Over time, those predictions can be tested. Hubble provides repeated global images. Amateur networks supply cadence. Archived Juno data constrains the deep state during key encounters. Future spacecraft could repeat microwave and gravity measurements. The storm's future becomes an experiment in planetary fluid dynamics, conducted on a scale no laboratory can reproduce. Yet one feature still threatens to confuse every test. The Great Red Spot is named for its color, and color is not vorticity. Before defining what death would look like, we need to ask what would happen if the red vanished while the storm kept turning. Jupiter's red, brown, orange, and cream tones come from particles that absorb and scatter sunlight differently across wavelength. The bulk atmosphere is mostly hydrogen and helium, neither of which paints a crimson oval. Common condensates expected in the upper weather layer are also pale. Something present in small amounts creates the color. Scientists use the general word chromophore for a material that absorbs certain wavelengths and therefore appears colored. The term names a function before it names a molecule. In the Great Red Spot, the responsible chromophore has not been conclusively identified. One leading candidate comes from laboratory work published in 2016. Researchers exposed ammonia to ultraviolet light and allowed the products to react with acetylene. The experiment created reddish compounds whose spectral behavior could reproduce important features of Jupiter's colors. Later studies showed that related models could fit spectra from the Great Red Spot and other colored regions when the particle size, amount, and vertical placement were adjusted. This is meaningful support. A candidate chemistry can be produced under laboratory conditions and can match light reflected from Jupiter. It is not a sample return. No instrument has collected one red particle from the Great Red Spot, carried it into a mass spectrometer, and returned a unique molecular label. The supply path is also difficult. Ammonia is abundant deeper in Jupiter, while acetylene is produced higher in the atmosphere from methane chemistry. The two ingredients must meet in the right pressure range, and the resulting particles must be created and maintained at a rate consistent with the observed haze. A 2026 microphysical study tested how the proposed upper chromophore haze could be sustained. Its simulations found combinations of particle charge, vertical motion, and material injection that reproduced the required haze. But the injection rates were greater than the supply available in standard models of ammonia and acetylene photochemistry. The result did not erase the successful spectral matches. It exposed an unresolved link between plausible colored material and the atmospheric machinery needed to keep producing it. Other candidates involve sulfur-bearing compounds, phosphorus chemistry, or more complex organic material. The data have narrowed the field, but the source of the exact red remains open. That uncertainty is why a phrase such as red means strong is scientifically fragile. We do not yet possess a simple relationship between pigment abundance and vortex energy. Color can change because the material changes, because particles move vertically, or because pale clouds form above them. The ultraviolet brightness variations seen during the 90-day oscillation illustrate this. The storm's core brightened in ultraviolet light when the oval was largest, a pattern interpreted as reduced haze absorption during that phase. One oscillation changed both geometry and the optical properties of the upper atmosphere. The surrounding South Tropical Zone also changes its brightness and haze. Contrast affects what an observer calls the edge. A pale red boundary against a bright background may look different from the same circulation beneath darker neighboring clouds. long records must separate photometric change from geometric change as far as the data allow. Oval BA provides a natural experiment. It is a smaller anticyclone south of the Great Red Spot. Its history can be followed through the merger of three white ovals around 1998 and 2000. The merged storm was initially pale. It became red by 2006, later faded toward beige, and in more recent Hubble images became somewhat redder again. The vortex did not come into existence at the instant it turned red. Its dynamical identity preceded the color change. It did not necessarily die when the color faded. Oval BA shows directly that a long-lived Jovian anticyclone can change its chromatic label while the circulation persists. The lesson travels back to the Great Red Spot. If its red material became pale over the next decade, the name might become awkward. The storm could remain dynamically recognizable through wind maps, altitude structure, or thermal contrast. Conversely, a red haze might linger after the circulation underneath had weakened. Chemistry has its own clock. This separation also sharpens the interpretation of 2019. A red blade leaving the oval is evidence that colored cloud material was stretched and transported. It is not direct evidence that hundreds of kilometers of rotating atmosphere detached with it. To establish that, scientists would need matching changes in the wind collar and deep anomaly. The color story gives us a fourth completed result. Redness is a tracer produced by uncertain chemistry. It can reveal vertical motion and particle distribution, but it cannot serve as a direct gauge of survival. Now return to the modern storm's beginning. The 2024 historical study did more than separate Cassini's permanent spot from the current Great Red Spot. It tested how a new giant vortex might have formed in the early 19th century. One possibility was merger. Jupiter contains many anticyclones, and Oval BA proves that three storms can combine into a larger one. If several large predecessors occupied the Great Red Spot's latitude, their collision might have produced the modern oval. The simulations struggled with that route. To build an object matching the early Great Red Spot, the parent vortices would themselves need to be very large, yet the historical record did not reveal them. The resulting shapes and rotation also did not provide the best match to the 1,831 observations. Another possibility was a superstorm, a major convective outbreak that generated a new circulation. Jupiter produces powerful eruptions. In the tested simulations, however, a single event formed vortices smaller or differently shaped than the historical protospot. The favored route began with the jets. A long disturbance formed between the westward flow to the north and the eastward flow to the south. The circulation cell was broad, shallow, and initially slow. Over time, it acquired coherence, became more compact, and rotated faster as it shrank. That scenario connects formation to the present contradiction. The Great Red Spot may have spent much of its modern life becoming shorter and faster. Shrinkage would not be a new terminal illness. It would be part of a 2-century evolution from an elongated circulation cell toward a compact vortex. But favored does not mean proven. Numerical experiments explore possible atmospheres. Their treatment of small-scale turbulence, moist convection, radiative transfer, and vertical structure is necessarily simplified. The initial state of Jupiter in 1831 is reconstructed from sparse observations, not measured by spacecraft. Other formation routes or combinations may remain possible. The value of the model is its testable narrative. It predicts that the early Great Red Spot should have had lower tangential velocity, and that rotation should increase as the vortex becomes compact. Historical wind measurements are too limited to trace every step, but modern observations can test whether continued geometric changes align with dynamical ones. The model also demonstrates why a long-lived vortex can die without being simple. If the old permanent spot vanished, Jupiter has already conducted the experiment once. A large storm can occupy the lane, persist across human generations, and then disappear from the record. Yet without measurements of its winds and depth, we cannot say which failure occurred first. Modern observers have enough instruments to do better. They can define several possible pathways to death and look for their distinct signatures. In one pathway, the high-speed ring weakens. Wind vectors that once formed a closed anticyclonic collar would slow, deform, or open into the surrounding jets. The interior clouds would no longer circulate as a coherent unit. Filaments could be carried away without returning. This would be direct dynamical evidence at the visible level. In another pathway, the vortex becomes unstable and divides. Instead of one persistent circulation, two or more smaller structures might form, each following a different trajectory. A temporary cloud split would not be enough. The wind field would need to show separate closed vortices that remain distinct. A third pathway involves vertical erosion. The visible top might retain a red oval for a time, while the deep microwave and gravity anomalies become shallower or weaker. Without repeat deep measurements, this route would be difficult to detect. It is a reason future close passes matter. A fourth pathway is merger or absorption. The Great Red Spot might encounter another major vortex or an altered jet configuration and lose its separate identity. The total circulation in the region would not necessarily vanish. It could be redistributed into a new storm or into the zonal flow. The final visible disappearance could occur in several ways. Red haze might fade as vertical transport changes. Pale clouds might cover the chromophore. The oval might stretch into filaments. The background zone could change contrast until the spot becomes hard to distinguish. None of those appearances alone specifies the dynamical route underneath. This is why the word death needs an operational definition. Planetary vortices are not organisms. They do not have a single instant when every process stops. A storm's identity is a pattern of organized flow. Its end may be gradual and scale-dependent. For this documentary, a strong diagnosis of Great Red Spot death would require sustained evidence across independent measurements. The visible wind field would lose a closed, coherent circulation. The high-speed boundary would weaken or break. The deep thermal or microwave anomaly would contract sharply or disappear. Those changes would persist across repeated observations rather than reverse in one oscillation. Color loss could accompany them, but color would not be the deciding test. This is an evidence synthesis, not a formal checklist, adopted by every planetary scientist. The literature does not provide one universally agreed death certificate for the Great Red Spot. Different studies focus on different levels and observables. The proposed test follows a basic principle. Claims about the whole vortex should be supported by measurements of more than its visible pigment. Such a test would also need a baseline. Wind maps must be made with consistent methods so that an algorithm change is not mistaken for atmospheric decay. Microwave passes must account for geometry and ammonia abundance. Gravity solutions must separate the vortex from deeper planetary harmonics and other atmospheric flows. Historical widths must preserve their larger uncertainties. Repeated observation is essential because the Great Red Spot oscillates. A deformed ring in one image could be a short interaction. A smaller width could be one phase of the 90-day cycle. A pale color could reflect haze altitude. Death would be a trend across cycles, not a single alarming frame. The standard may sound demanding. It should. The stronger the public claim, the more evidence it needs. Saying the spot is smaller requires a measured boundary. Saying the vortex is changing requires a wind, thermal, or depth record. Saying it will disappear by a certain year requires a validated model of future evolution. Current science supports the first two at varying levels. It does not support the third. At this point, the original contradiction has become more precise. A contracting long axis and a faster high-speed ring are not opposing verdicts. They are two variables in a system seeking or losing balance. The deep vortex shows that upper cloud appearance is incomplete. The oscillation shows that short-term width can reverse. The chemistry shows that red color has its own behavior. The interaction models show that the environment may feed or starve the vortex. None of this proves permanent survival. It replaces a countdown with competing physical futures. The first future is stabilization. The oval becomes shorter and rounder until it fits within the surrounding jet lane. Its average dimensions then fluctuate around a smaller value. The high-speed ring remains coherent, and the deep anomaly persists. Color continues to vary. In this future, the Great Red Spot survives in a form that would look modest beside its 19th century ancestor, but still enormous beside Earth's weather systems. The second future is continued evolution without immediate collapse. The long axis keeps contracting, perhaps at a variable rate, while wind speeds, depth, and color adjust. The storm could remain identifiable for decades, even as its geometry changes. No sharp line would separate healthy from dying until the circulation began to lose coherence. The third future is eventual decay. The vortex's energy sources and environmental support no longer balance its losses. The wind collar weakens, deep structure erodes, and the oval is absorbed into the surrounding jets, or fragments into smaller storms. This outcome is physically possible. The likely disappearance of the permanent spot and the observed loss of giant vortices on Neptune make immortality untenable. The fourth future is transformation. A major interaction changes the vortex so thoroughly that debates about identity begin. If it merges, divides, changes latitude, or develops a new wind structure, observers may disagree over whether the Great Red Spot survived or produced a successor. Nature does not have to preserve the categories used in our names. Which future occurs depends on mechanisms still being tested. The jet band stabilization idea favors the first. Reduced feeding by smaller vortices could encourage the second or third. An unexpected interaction could produce the fourth. Current data do not assign reliable probabilities. This answer may feel less satisfying than a date, but it is more useful. It tells us what to measure and what new evidence would change the conclusion. A date ends curiosity. A diagnostic creates a research program. That program already exists in pieces. Hubble's Outer Planets Atmospheres Legacy program, known as OPAL, returns to Jupiter and the other giant planets with consistent global imaging. The project provides yearly maps that can be compared across a decade or more. It captures winds, colors, haze changes, and storm evolution with the same observatory. OPAL is not continuous surveillance. Jupiter rotates in under 10 hours, and its clouds evolve between visits. Annual maps can reveal long trends, but may miss a week-long interaction. Dedicated campaigns like the 90-day sequence add cadence when a specific question demands it. Ground-based observatories fill another part of the timeline. Large professional telescopes can observe infrared wavelengths unavailable at the same resolution to many amateurs. Spectroscopy can trace gases and aerosols. Thermal imaging can map temperatures and cloud heights. Radio telescopes sense ammonia and deeper structure across broader regions. Amateur observers provide frequency and geographic coverage. A telescope in one country may lose Jupiter to daylight, while another gains it. Coordinated databases allow researchers to identify an outbreak, a flake, or an approaching vortex, then request time on more specialized instruments. Spacecraft supply the measurements Earth cannot easily make. Juno's archive retains microwave, gravity, magnetic, infrared, and visible data from close passes. Even after a particular encounter, improved models can extract new information from old signals. A future mission could repeat depth measurements after years of additional shrinkage and ask whether the deep vortex followed the visible boundary. The most valuable future observation might not be a spectacular close-up. It might be a well-calibrated series made in the same way for 20 years. The high-speed ring trend was detectable because Hubble provided consistency. The annual increase was too small for a casual comparison. Precision turned a slight change into evidence. The same principle applies to the storm's width. Researchers need a defined boundary, uncertainty estimates, and multiple wavelengths. If a red outline contracts while the wind collar does not, the discrepancy is a result. If both contract together, that is a different result. If microwave depth remains constant, the vortex may be changing aspect ratio. If depth declines as width declines, a fuller erosion may be underway. One can imagine a future chart with 4 synchronized panels. The first shows visible long axis length. The second shows maximum and average wind speed in the high-speed ring. The third shows color and haze optical depth. The fourth shows the depth of the thermal and gravity anomaly. Only when those records are aligned can the life cycle be reconstructed with confidence. The chart would still not explain everything. cause and correlation remain separate. A decline in smaller vortex encounters might accompany shrinkage without causing it. Jet changes might result from broader atmospheric evolution. Internal heat flux and moist convection might alter the storm from below. Models would still be required. Yet models improve when observations force them to match several variables at once. A simulation that reproduces width but not wind speed is incomplete. A model that matches cloud top motion but creates the wrong depth can be rejected or revised. The Great Red Spot becomes a benchmark for atmospheric physics under rapid rotation and deep stratification. That physics extends beyond Jupiter. Giant exoplanets cannot be resolved into detailed cloud maps with present instruments, but their brightness can vary as storms and bands rotate in and out of view. Understanding how color, cloud area, and deep circulation relate on Jupiter helps researchers interpret those distant signals. A changing spot on an unresolved world might reflect chemistry, dynamics, or both. The Great Red Spot also tests the universality of weather concepts. Earth's cyclones draw energy from warm oceans and are disrupted by land. Jupiter's anticyclone lives inside opposing jets with no comparable surface boundary. Neptune's dark vortices migrate and vanish over a few years. Oval Ba formed by merger and changed color. Across these worlds, the word storm covers systems with different energy sources and life cycles. What unites them is organized flow. A storm exists as long as the circulation and associated pressure or thermal structure remain coherent enough to distinguish from the background. Appearance helps us find it. Dynamics tells us what it is. This gives the shrinking Great Red Spot a consequence larger than its own future. It teaches us how to identify an object made of motion. A mountain can lose snow and remain the same mountain because rock fixes its identity. A vortex has no fixed material. New gas enters and old gas leaves. Its identity persists as a pattern. That pattern can change dimensions without becoming a different object. It can change color without losing rotation. It can exchange energy with smaller systems. It can breathe within a confining lane. To ask whether it is dying is to ask whether the pattern is losing the ability to reproduce itself through time. We cannot answer that by following one parcel of hydrogen. The parcel will not stay. We answer by tracking structure, the closed wind field, the pressure anomaly, the vertical depth, the interaction with jets, and the recurrence of the shape after disturbances. This is also why the modern storm's identity can be traced back to 1831, despite constant material replacement. The same circulation pattern occupies the same latitude band, drifts in a continuous record, and evolves in size rather than appearing as unrelated ovals. The identity is dynamical and historical. The Permanent Spot Challenge shows the limit. A 118-year observational gap breaks continuity. Similar latitude is not enough to prove the same vortex. Without a chain of positions, motions, and dimensions, identity becomes inference. If the modern Great Red Spot faded from view for a decade, future astronomers would face a similar problem. They would search infrared and microwave data for hidden circulation. They would compare drift rates and jet interactions. If a red oval later appeared in the same lane, they would ask whether the old vortex returned to visibility or a new one formed. Our present instruments may prevent such ambiguity. Even a pale storm can be followed through winds and thermal contrast. The Great Red Spot could lose the color in its name and remain an observable vortex. Now consider the opposite. Suppose the red oval stays bright, while wind tracking shows the high-speed ring opening into surrounding flow. The visible pigment might persist as a stretched cloud for several rotations. A beautiful red feature could outlive the organized storm that created it. Appearance would lag dynamics. This possibility is not a prediction. It is a reminder that endings can be asynchronous. One layer can retain memory of another. Chemical particles survive for a time after their source changes. Deep circulation can persist after upper clouds reorganize. A diagnosis must specify which layer has ended. For public language, the safest hierarchy is simple. The Great Red Spot is shrinking describes a measured geometric trend. The Great Red Spot is changing describes several measured trends in size, wind, color, and oscillation. The Great Red Spot may eventually disappear is a physically reasonable possibility. The Great Red Spot will die by a named year is not supported by current evidence. This hierarchy also helps us compare the leading explanations for the shrinkage. Each explanation predicts a different relationship among width, wind, depth, and the surrounding atmosphere. That means the problem can be approached as a set of tests rather than a contest of dramatic phrases. Begin with geometric adjustment inside the jet lane. If the Great Red Spot is overfilling the space permitted by the surrounding winds, its long axis should contract as the vortex becomes less elongated. The north to south extent should remain constrained. The latitude should stay stable. Once the oval fits the lane, the average dimensions should level off, even though short oscillations continue. The Hubble record already contains parts of that pattern. The storm has become rounder. Its latitude is stable. The dedicated campaign caught the oval squeezing between neighboring jets. What the record does not yet contain is the predicted endpoint. No plateau has been observed long enough to establish a new equilibrium. Now consider reduced feeding by smaller vortices. If that mechanism dominates, the red spot should grow or strengthen after frequent favorable encounters and shrink during long periods with fewer transfers. The type of encounter matters. An anticyclone rotating in the same sense may merge and add circulation. A cyclone or a vortex on a different trajectory may strain the boundary instead. Counting every nearby spot without classifying its dynamics would blur the prediction. A good test would combine global maps with a catalog of neighboring vortices. For each one, researchers would measure size, rotation, latitude, and closest approach. They would then compare the Great Red Spot's area and wind ring before and after the interaction. A repeated statistical relationship would support the feeding mechanism more strongly than one spectacular collision. The 2024 simulation provides a reason to run that test. It does not substitute for the observational catalog. Models can hold most variables constant and change only the frequency of interactions. Jupiter cannot. On the real planet, Jets, convection, wave activity, and haze all change together. A third explanation focuses on internal circulation. The vortex may lose energy through turbulence and radiation, while vertical motions return energy from deeper levels. If that balance shifts, width and wind could change even if the external storm population stays constant. This hypothesis predicts vertical signals. Temperature contrasts, ammonia distributions, cloud height, or microwave brightness might evolve with the size. A vortex becoming shallower could lose horizontal scale. A vortex maintaining depth while becoming narrower would change its aspect ratio instead. The existing Juno encounters offer only a few deep snapshots, so the time dimension is missing. Researchers can compare different parts of the storm and different vortices, but they cannot yet build an annual depth curve matching Hubble's width curve. A fourth explanation involves broader jet evolution. The Great Red Spot's lane is created by planet-circling winds. If the speeds or latitudes of those jets change, the available space and shear around the vortex also change. The storm may respond even if its internal energy source remains the same. This idea demands global measurements. It is not enough to track the two boundaries nearest the red oval. Researchers must map the wider southern atmosphere and distinguish a local response from a planet-wide shift. Hubble's consistent global maps are especially valuable here because they record the context at the same time as the storm. These explanations can operate together. A changing jet can redirect smaller vortices, altering the Great Red Spot's diet. A more compact shape can change the way the storm interacts with the jets. Vertical circulation can influence haze, making the visible outline respond differently from the wind boundary. This coupling is why the search for one cause has remained difficult. The storm is not a machine with one failing part. It is a pattern maintained through exchanges across scale. Scientists often make progress by looking for a variable that one hypothesis changes and another leaves alone. Depth is one such variable. Encounter frequency is another. The ratio of visible width to wind collar width may be a third. The phase relationship between size and speed during the 90-day oscillation may offer a fourth. During the Hubble campaign, the Great Red Spot did not merely change size, its speed changed with the squeeze. If future campaigns repeat the same phase relationship, models must reproduce it. If the relationship drifts, the supposed 90-day cycle may be only one expression of a more variable interaction. Color adds yet another independent clock. The ultraviolet core became brightest when the oval was largest during the observed cycle. A successful model of the oscillation must explain not only the shape and motion, but also the haze response. That requires a connection between dynamics and vertical particle distribution. The demand for multiple matches protects the science from a common trap. A model can often reproduce one curve by adjusting parameters. Reproducing size, wind, color, and depth with the same physics is harder. It is also more persuasive. The Great Red Spot scale makes direct laboratory replication impossible. Earth laboratories can rotate tanks of fluid, vary stratification, and create vortices between jets. Those experiments revealed general behaviors such as merging, filament shedding, and confinement. They cannot match Jupiter's full range of pressure, composition, rotation, and size. Computer models bridge part of the gap. Some represent a thin weather layer. Others include vertical structure and moist convection. High resolution captures smaller eddies, but requires more computing power. Simplified chemistry allows long dynamical runs, but cannot predict color in detail. Every model selects which part of the storm to make realistic. Observations decide which simplifications remain useful. If a shallow model reproduces horizontal winds but conflicts with Juno's depth, it needs revision. If a deep model produces the right depth but the wrong oscillation, it is incomplete. The storm forces theory to work across dimensions. There is a deeper reason this diagnostic matters. A vortex is an example of a coherent structure in turbulence. Jupiter's atmosphere is not calm material disturbed by one storm. It is turbulent at many scales. Jets, waves, convective plumes, and vortices continuously interact. The Great Red Spot persists by maintaining recognizable organization inside that restless background. Coherence does not mean perfect isolation. Gas crosses observational boundaries. Clouds form and evaporate. Smaller eddies are absorbed and expelled. The vortex remains coherent if its large-scale circulation continues to organize those changes around a stable center and a closed wind pattern. Death, in that language, is loss of coherence. The flow no longer returns around one center. The boundary can no longer resist stretching by the jets. The thermal and compositional anomaly disperses into the background. The name ceases to identify a persistent pattern. This definition handles gradual endings better than color or size. A vortex can lose coherence in stages. The upper clouds may become disorganized while the lower circulation persists. The deep anomaly may weaken while a shallow remnant survives. Different instruments could disagree for a time because they are observing different stages. Neptune offers an instructive contrast. Voyager 2 found a great dark spot in 1989. The feature was comparable to Earth in scale and accompanied by bright high clouds. When Hubble looked in 1994, that southern storm was gone. Later dark spots appeared at other latitudes, migrated and dissipated. Hubble's multi-year monitoring indicates that Neptune's dark vortices commonly last years rather than centuries. Some drift toward the equator, where the surrounding wind environment can tear them apart. Their disappearance proves that a giant planet vortex does not need landfall to end. Yet Neptune cannot provide a direct timeline for Jupiter. Its atmosphere has different composition, heat flow, stratification, jets, and vortex behavior. The Great Dark Spot was also observed at close range only during a brief flyby. Its deep structure was not measured with the same combination of microwave and gravity methods. The valid comparison is narrower. Large vortices on fluid planets can lose identity. Migration and changing environmental shear can matter. Visible dark or bright companions can evolve differently from the hidden circulation. Beyond that, Jupiter must be diagnosed on its own evidence. Oval BA provides a closer Jovian comparison. Its formation by merger proves that vortex identity can emerge from several predecessors. Its color changes prove that pigment and circulation can separate. Its repeated passes near the Great Red Spot show how two anticyclones can share a planet while occupying different lanes and drifting at different rates. Oval BA is smaller and younger. It does not tell us the Great Red Spot's future. It gives scientists a second long-lived anticyclone under related planetary conditions, a kind of natural control case. Features shared by both may reveal general Jovian vortex physics. Features unique to the Great Red Spot may be tied to its exceptional size, latitude, or history. The old permanent spot supplies a third comparison, though its evidence is sparse. If it was a separate vortex that disappeared, Jupiter's same broad latitude region has produced at least two giant long-lived spots across the telescopic era. That possibility changes how we think about permanence. The lane may be capable of generating successors even when individual vortices end. In that case, the Great Red Spot is not a once-only blemish on a static planet. It is one long chapter in an atmospheric environment that can organize giant vortices, maintain them, and eventually replace them. The 2024 origin simulations support that environmental view. A disturbance between jets may have condensed into the modern storm without requiring a singular impact or solid obstacle. The atmosphere itself supplied the instability, the confinement, and the route toward coherence. If the modern vortex dies, the lane will remain. The jets may eventually generate another large circulation. A future observer could see a new oval and face the same identity question that separates Cassini's permanent spot from the storm seen in 1831. This creates a consequence beyond the fate of one icon. The Great Red Spot is a test of whether longevity belongs mainly to an individual vortex or to the atmospheric architecture that keeps creating favorable conditions. The answer may involve both. The current pattern has its own continuous history, while the jet lane provides a durable stage. Long observation is the only way to separate them. A spacecraft flyby gives detail but not life cycle. A century of drawings gives life cycle but limited physics. Hubble bridges part of the gap with repeated precision. Juno adds depth during selected moments. Amateur networks supply cadence. No single observer owns the complete record. That record also teaches caution with rates. Suppose a width decreases by a certain number of kilometers per year over 1 decade. A linear extrapolation assumes the same rate, the same boundary definition, and no new equilibrium. An exponential extrapolation assumes a different mechanism. A model based on jet confinement predicts flattening. A feeding model predicts changes when the environment changes. Choosing a mathematical curve is already choosing a physical story. Without evidence for the mechanism, a date calculated from the curve is not a forecast. It is an illustration of an assumption. This is especially important near a scale comparable with Earth. Public descriptions often say Earth could fit inside the Great Red Spot, or that the storm has become smaller than Earth in one dimension. The comparison changes depending on which axis and which boundary are used. It is visually powerful, but Earth is not a death threshold. A vortex does not become unstable because its width crosses one planetary diameter. The meaningful thresholds are dynamical. Does the high-speed ring remain closed? Is the vortex wide enough to resist the surrounding shear? Does its depth support the observed circulation? Can it maintain a thermal and compositional anomaly? Do interactions add or remove circulation faster than the storm loses it? Those thresholds are not yet known as simple numbers. They may depend on several variables at once. A smaller storm can survive if it is compact and well confined. A larger storm can deform if the jets or neighboring vortices strain it. This returns us to the Hubble team's stabilization proposal. The phrase "smaller but stable" is not a comforting guess. It is a physical possibility based on the relation between the oval and the latitude band. The team expects the jets to hold the vortex more effectively after it shrinks within the lane. Future data can reject that expectation. If the storm passes the predicted geometry and continues to contract without leveling, the model needs revision. If the latitude changes or the wind ring weakens, stabilization becomes less likely. If the average size flattens while oscillations persist, the proposal gains support. Science does not protect a favorite outcome. It turns the outcome into a condition that observations can test. That hierarchy protects the wonder rather than reducing it. The true story is not that a giant storm has a timer. It is that a 2-century vortex can contract, accelerate at its edge, oscillate, exchange energy with smaller storms, change its haze, and extend 500 kilometers below the clouds while scientists try to understand which changes belong to one mechanism. The storm is not a relic frozen since the first telescope. It is an active system. Its longevity comes with motion, deformation, and uncertainty. Return once more to the Hubble measurements that opened the episode. Over 11 years, the high-speed ring became faster by up to 8%. Over more than a century, the oval became smaller and rounder. Over 90 days, it squeezed in and out. These are 3 clocks, nested within the same atmosphere. The longest clock records evolution across generations of observers. The middle clock records a subtle wind trend, visible only through consistent technology. The short clock records breathing within one season. A 4th clock may govern color chemistry. A 5th may govern exchanges with neighboring vortices. A 6th may govern changes in the deep structure. Calling all of them death compresses a rich system into one word. Separating them reveals the experiment Jupiter is performing. The ending answer can now be stated without evasion. Jupiter's great red spot is unquestionably shrinking in its long visible dimension. It is also becoming rounder. Its fastest outer winds increased during the Hubble interval from 2009 to 2020. Juno found that the vortex extends hundreds of kilometers below the cloud tops. Hubble found that its size and shape oscillate over about 90 days. Models show that surrounding jets and smaller vortices can influence its dimensions. Together, these facts describe a storm in transition. They do not establish that the circulation is currently undergoing irreversible collapse. They do not support a year when the red oval will disappear. The great red spot may stabilize at a smaller size. It may continue to contract. It may eventually decay or transform. All three remain live outcomes because the mechanisms controlling its size are not fully known, and its deep evolution cannot be monitored continuously. What would change that answer is sustained convergence. If repeated wind maps showed the high-speed ring weakening and losing closure, if deep measurements showed the vortex becoming shallower, if oscillations no longer returned the oval to a coherent form, and if those changes continued across years, the case for death would become strong. A smaller red patch by itself cannot carry that claim. For now, Jupiter has not given us a countdown. It has given us a lesson in how science recognizes a thing that has no fixed substance and no solid edge. The great red spot is made of gas that is always moving through it. Its color is made by particles whose identity remains uncertain. Its boundary changes with the instrument used to find it. Its history begins not with a birth certificate, but with a drawing from 1831. Its depth is inferred from microwaves and a tug on a spacecraft measured across hundreds of millions of kilometers. And still, the pattern endures. It is smaller than the vast oval watched in 1879. It is not the timeless object old legends promised. It may not survive forever. But the evidence we have today describes a coherent, deep, evolving vortex, not a storm with a known date of death. The next time a new image shows the red oval narrower, paler, or shedding another blade of cloud, the right question will not be how many years remain. The right question will be which layer changed. Did the color move, or did the winds weaken? Did the cloud outline contract, or did the deep vortex erode? Did a short oscillation squeeze the oval, or did a long trend accelerate? Did a neighboring storm steal energy, or deliver it? Those questions are slower than a countdown. They are also how Jupiter will finally answer. Not through one perfect image, but through agreement among records made by different instruments at different depths. The answer will arrive as a pattern of changes that persists long enough to outrun the storm's ordinary breathing. Until then, uncertainty is not an empty space around the story. It is the boundary that keeps the story true. And on Jupiter, that boundary is still moving with the storm.